Hi, so today we're going to be covering drawing chemical structures in organic chemistry. Drawing chemical structures is really a foundation of how you are going to first understand a question as it's presented to you, but also how are you going to communicate an answer on a quiz or an exam to your instructor. So in order to really understand chemical structures, the way I would recommend you approach it is actually with a piece of paper and a pen in your hand. Because drawing chemical structures, understanding chemical structures, is as much a physical skill as it is an intellectual skill. And if you can get to the point where you're so fast with drawing them that you can just bypass your brain and go right to drawing the structure, you'll be in great shape and it'll save you a lot of time on exams and whatnot, agonizing over what something means. Okay, so let's go ahead and get started. When you're taking organic chemistry, you're often going to encounter a chemical structure like the one you see below of caffeine. But what does it mean? What are all the connectivities? Where are the hydrogens? Where are the carbons in this structure? So there's several ways that you can represent a molecule. The first way, which you learned in general chemistry, is with the formula. But that formula could actually be drawn several ways. And that's another topic for another video, which is on constitutional isomers. But aside from the formula, there's really three ways that you can draw a chemical structure. There's the condensed form, there's the skeleton form, and there's the line bond structure. So each of these structures represent the same molecule with the same connection of atoms, but there are just three different ways to show how that can occur. So the most important one we're going to cover is the skeleton structure. The thing you'll notice about the skeleton structure is that the carbon and hydrogens are not drawn. Each intersection represents a carbon, or each end of a line. Functional groups are drawn, otherwise you wouldn't know whether you had another kind of atom there or not. And each line represents a carbon-carbon bond. So when you see one line, it's a single bond. Two lines would represent a double bond, three a triple bond. So let's look at an example of going back and forth between these three kinds of chemical structures. The structure on the left is showing a skeleton structure. It's a 4-carbon chain. So if you count from left to right, each end of a line and each intersection represents a carbon, and you have 4 carbons. So 1, 2, 3, 4. Each carbon has a set of hydrogens attached to it. If you look in the center is the line bond structure. The line bond structure gives you all the detailed information about who's connected to who, which carbon is connected to which carbon, how many hydrogens each carbon has, and which carbon is connected to the amine group, the NH2 group. The last one, the one on the far right, is showing the condensed structure. The condensed structure is a shorthand way of representing how all the atoms are connected. In this form, we write out the hydrogens that are associated with each carbon to the right of each carbon. Now that doesn't mean that the hydrogens are between two carbons, it just means that they're associated with their particular carbon. So for example, the CH3 group on the left side of that molecule, right here, these 3 hydrogens are associated with this carbon on the far left. These 2 hydrogens are associated with this carbon, this hydrogen associated with this carbon, and then these 3 hydrogens are associated with this carbon. An important thing to remember when you're talking about any of these structures is that non-bonding electrons are still there even if they're not drawn. So for example, in this particular structure, whether you're looking at any one of these 3, the nitrogen is going to have a pair of non-bonding electrons, and they may be shown or they may not be shown, but it's important that you know they're still there. Here's another example of going back and forth between the 3 kinds of structures. This molecule acetone, shown in the skeleton form on the far left, is a CH3 group, and then a carbonyl in the middle with a carbon-oxygen double bond, and then a CH3 group. Shown in the middle is the line bond structure, and now here you can see the detailed information that's going on. So for example, this CH3 group here on the far left represents this end of a line right here. This carbon here bonded to the oxygen in a double bond represents the carbon right here. And the CH3 group on the right is represented by the end of the line in the skeleton structure. If you look on the far right, here we have the condensed structure. Again, it's a shorthand way of representing any of these two structures on the left. And the most important thing about condensed structures to remember is that the hydrogens are drawn to the right of the carbon that they are attached to. Skeleton structures are particularly useful when you're drawing rings. If you try to draw a line bond structure or condensed structure of a ring, it gets messy pretty quickly. So it's difficult to draw those using the other forms, and often we'll invert functional groups to show connections. So as you learn about the types of chemical structures, you're going to get questions on your first test or quiz, which are going to test your understanding of chemical structures. So what I'd like to do is walk through two kinds of questions that you can expect to encounter. The first kind of question is like this one, which asks you how many hydrogens are in each carbon, and then you're given a skeleton structure. So here's your skeleton structure below, and you're being asked how many hydrogens does each carbon have? Well, in order to answer this question, the first thing you need to do is figure out where all the carbons are, and the second thing you need to do is figure out how many hydrogens are needed to satisfy the octet rule. So let's look at that chemical structure, and with arrows we'll identify where each carbon is. So again, in a skeleton structure, the end of a line or any intersection represents a carbon. So I've drawn arrows to show where you have a carbon in the structure. The next thing you need to do is you need to look at the structure and look at each carbon. And each carbon needs to have an octet, 8 electrons or 4 bonds. So what you do is you break it down by how many bonds that carbon is already participating in. For example, the carbon on the far left is participating in 1 bond with another carbon. Therefore, it's going to need 3 more bonds to satisfy the octet rule, or 3 hydrogens. And then you go about it through the similar kind of logic. The next carbon in is participating in a bond with 1 carbon going to its left and a double bond with the carbon going to its right. So it's already participating in 3 bonds. So it needs 1 more bond to satisfy the octet rule, or 1 hydrogen. And you can go through the example in this manner and figure out how many hydrogens each carbon has. The central carbon is participating in 4 bonds already. It's got a double bond and it's got 2 single bonds. That's 4 bonds or 8 electrons, so there would be 0 hydrogens attached to that carbon. The next carbon, the one that's participating in a bond with the OH, is going to have 2 hydrogens. Another kind of question that you can expect to encounter is where you're asked to convert a condensed structure to a skeleton structure, or to convert a line bond structure to a skeleton structure, or vice versa, go from a line bond, or excuse me, from a skeleton to a line bond structure. So let's take this example. You have a molecule below and you're asked to convert it to a skeleton structure. Well, the answer is going to be, if it's a ring, what you want to do is count out how many carbons are in the ring. So in this example, we have 6 carbons in the ring. If you count them up, you have 6 carbons in the ring. So the simplest thing to do when you're confronted with a ring structure is to simply draw a geometrical shape that corresponds to that number of carbons. So 6 carbons would be a hexagon. So what you're going to do is draw a hexagon, and each intersection will represent a carbon. Then what you're going to do is you're going to attach lines to represent each of the bonds. So we have our hexagon is where we start from. Those are our 6 carbons in the ring. There's a double bond between the top carbon and the carbon to the right, which we're going to also represent. There's a methyl group coming off to the left, which is represented by a single line, and the end of that line represents a CH3 group. There's an ethyl group coming off to the right, represented by a CH2 and CH3 group. So these are the kinds of questions you can expect, and drawing chemical structures is going to be super important, so the best advice I have is to keep practicing.